this resonating valence bond state in the spin half chain is that I have some form of a quantum superposition of singlet formation on all length scales. All length scales because I see very low energy excitations in the system. So there must be some very weakly bound singlets that are available for me to break in the system. So this is, we should imagine some sort of a superposition of many ways that I can form singlets on the chain, and the excitations then have this two-particle character in that they are associated with breaking the singlet and liberating therefore two spin half degrees of freedom that can then travel through the quantum fluctuating state of singlets. So these are not bound to each other anymore because they live in this quantum fluctuating medium. I'm not able to individually create one of these particles in the scattering process because each particle carries spin half, and I'm not able with the neutron to deliver spin half, h bar half angular momentum into the system because neutron comes in with spin half, but it needs to leave the system for me to observe it again. Therefore, it cannot have deposited its spin half degree of freedom. I can only interact with a pair of spin 1/2 degrees of freedom to have a spin flip scattering event that I can actually detect with the neutrons. So that's some sort of rough picture of what we think about in a quantum magnet with resonating valence bonds. Now, for the spin half chain, this is on very firm theoretical footing. Not this particular picture, but there's a lot of knowledge about the spin 1/2 antiferromagnetic chain. Much less so about these higher dimensional spin systems. But what I could say is that we would like to go for high dimensional spin systems that somehow sit near a quantum critical point. This is the case for the spin half chain. What's shown here is the Hamiltonian for an alternating spin chain where one is varying, and you can read more in this beautiful paper, where one is varying the bond alternation so that either you have an odd bond singlet state or an even bond product singlet state. But right here in between, you have this sort of inability to determine which of these is going to be the low energy state, and that becomes a quantum critical point. And it's at this quantum critical point that I have these independent spin and type excitations available, because I do not have the broken translational symmetry associated with being on the left or the right hand side. So these spin half degrees of freedom can travel through the quantum fluctuating medium. So we need to somehow create, or we would like to create experimentally a system of spin half degrees of freedom that sits at such a quantum critical point. So that brings me to frustrated magnetism, because we need some device in order to suppress the formation of a nail-type long-range antiferromagnet. And that device is going to be competing interactions or frustrated interactions. And just to introduce this concept, I'd like to juxtapose the case of a non-frustrated magnet with a frustrated magnet. So for a square lattice antiferromagnet, this is not, if I only have near-neighbor interactions, this is not a frustrated system. So if I lay down one spin in some fictitious low energy, low temperature situation, then I have to somehow, I'm now prescribed what I should do with the neighboring sites, and then everything propagates from there outwards, and there's actually just a single low energy state that sort of unfolds once I prescribe one spin on this lattice. Of course, this is kind of a semi-classical picture of the whole thing, which is questionable, but it's the way we'll kind of get into this aspect of frustration in the system. So that's the unfrustrated case. And if we think of this lattice, which we regard as frustrated, it's a kagome. It's called the kagome lattice. And I'll say a few more words about those kinds of lattices. But what happens there if I lay down one spin as I did there, then if I imagine having antiferromagnetic interactions, then this would be a configuration that would be a low energy configuration. It's not really ideal for any of the antiferromagnetic interactions that I have, but it's the best I can do. I can actually do a lot of things that are equivalent. I can rotate this pair of spins around a vertical axis, and all of those at a semi-classical level will have the same energy. And in fact, if I go and lay out a kind of a ring of kind of a closed loop of spins that are parallel to each other, then all of the stuff that's inside, I can actually rotate that around this axis. And I won't, if I have Heisenberg spins, then there's no dependence on the energy of the system to the angle of rotation around this vertical axis. So there's a lot of kind of floppy, low energy degrees of freedom that we have in this system, and that has the potential to break down the formation of a nail state on this lattice. Okay, so we're going to actually focus on those types of spin systems which we could describe as corner-linked simplexes. So we'll have units which in this case were triangles which are linked on the corners. That tends to give rise to this floppiness, the weak connectivity of the lattice. But you can also do it with tetrahedra, where you have 1, 2, 3, 4 spin degrees of freedom, but then linked by corners. That also leaves a lot of degeneracy associated with the arrangement of spins on the tetrahedron in such a way that you can sort of satisfy the interactions as well as possible without having a long-range ordered spin configuration. That's the kind of spin system that we would like to look at. Okay, so first let's start off with the kagome system, and since we're doing experimental physics, we need to look at specific materials. And the compound that we will look at is Herbert smithite. This was introduced by Young Lee and Dan Nocera from MIT, and we collaborated with them on some of the neutron experiments on this material. The compound is extremely unusual, I will say. There's several very interesting aspects of this material that are perhaps not reproduced in any other system that we know of. They're reproduced within, when people from different groups make this compound, they have these properties, but it's very difficult to point to compounds that have these particular properties. What are those properties? Number one, no indications of a phase transition down to the lowest temperatures that people can access, down to millikelvin temperature range, even though, as measured by the Curie-Weiss constant, the exchange interactions are antiferromagnetic and quite strong in this compound. So even to temperatures much, much less than that energy scale, there's no phase transition taking place. So that's actually very unusual. There's not even a glossy transition. So if you look at very low field squid magnetometry, there's no zero field cooled hysteresis that shows up. And also if you look at things like NMR, you also don't have this taking place. So really no freezing. That's very, very strange actually. And I'll try to answer why it is that this compound behaves like this, or give you some indications of that. Now, what does the structure look like? It's basically a stacking of alternating kagome planes and triangular lattice planes in this shifted configuration. And on these triangular lattice planes that are in between the kagome layers, there was supposed to be no magnetism at all. But it turns out that there is actually a 15% occupation of that sublattice by magnetic copper spin half degrees of freedom. So those are coming with us for the ride, and no one knows how to get rid of them, unfortunately, right now. If we could, if someone knew, they would definitely do that. But for now, we have a mixture of these completely filled kagome layers with spin 1/2 with such dilute triangular lattice layers with dilute concentration of spin 1/2 degrees of freedom. Okay, this is how the inelastic neutron scattering data look. And what's shown here, I think that might be the first example I give you of that, is a slice in momentum space. So this is momentum space variables of the inelastic neutron scattering at certain fixed values of energy transfer. Okay, so it's a little bit of a strange thing. Normally I've been showing you momentum and energy, and the dispersion relation lives in that plane. In this plane, if I was to have a conventional long-range ordered magnet, what I'd see in this plane would be very sharp traces where I match the dispersion relation for spin wave excitations. So there'd be little rings of scattering that would be emanating from Bragg peaks. But remember, this system does not have any Bragg peaks. It doesn't have any long-range order. So there's no place from which the dispersive spin waves can emanate. And indeed, we don't see anything that relates at all to spin wave excitations in the system. What we do see are these extended structures in momentum space, which actually extend much beyond the Brillouin zone. So this hexagon is the Brillouin zone, and you see that these structures are much extended beyond that. These structures are quite rigid. They persist up to high energy transfer. And what they remind us of is the transition matrix element for a singlet to triplet excitation. Remember I talked about that for the copper nitrate system. There's this 1 minus cosine QD term. That same term can actually account for these kinds of momentum dependencies. If I take the pairs of spins on the kagome lattice, and there are 3 different orientations of those, and then I draw this function 1 minus cosine q dot d for those 3 different oriented spin 1/2 pairs, then I get structures that look exactly what as what I see experimentally. So it means that I'm seeing, or what is seen here is the experimental signature of singlets being broken and forming triplets instead. And this is exactly what we would expect if we had a resonating valence bond state. As the spinon moves through the fluctuating soup of singlets, I'm breaking singlets and I'm picking up the structure factor associated with this singlet to triplet transition. Question?
So I don't get so H0 minus J.
Oh,
is this the X and Y component of the momentum transfer?
Yes, yeah. And it's indexed in a hexagonal reciprocal lattice, which is convenient. But you could also just call it QX and QY.
And why is it useful to plot the Broholm zone on top of that?
Oh, these black lines?
Yeah.
The Brillouin zone is some important entity in thinking about reciprocal space. And if I was to have a long-range ordered magnet, then I would have spin wave dispersion relations. And those dispersion relations would have the periodicity of reciprocal space. And so I normally expect things to kind of repeat as I go from one zone to another. Now this is modulo structure factors. They actually can vary across the zone. But in this case, I have nothing which is kind of following the periodicity of the underlying Brillouin zone. I have simply a structure factor dominating the entire scattering. I do have, and this we were happy to see, I do have the rotation axis reproduced, so I know that this is somehow tied to spins that live on the lattice. Okay, so actually this picture here is a calculation of the structure factor for low energy spinon type excitations in a kagome antiferromagnet, which was carried out before the neutron scattering experiment was done by Oleg Chernyshov, my colleague, and his collaborators. And they said this is what you should see. And I really had not expected that at all, but in fact it was what came out. This is really very unusual. Just like I mentioned that the thermodynamic features of the Herbert-Smithite compound are very unusual. Likewise, this scattering pattern is something that is very seldom, very unusual to see in a two-dimensional dense spin 1/2 system. Now I'm going to look at the momentum energy dependence of scattering. So remember with these modern instruments, we collect all the momentum space, all of energy space. So we have the data kind of sticking out of the board if you imagine energy coming out. So I can show you the data as a function of momentum and energy along this cut and along this cut. And so one of these cuts is sort of along the line of high intensity, along this line. And the other cut goes through a lake where the intensity is very low. So this is low intensity regime, this is high intensity regime. So let's see what those two cuts look like. And what we find for a cut, which is this one that goes through the lake, we find that this lake, if you will, persists up to a very high energy. So there's really, these structures are persist in energy, and that indicates and is consistent with the fact that the energy scale for this spin system is actually in the 30 to 40 millielectron volt range. So this is really the low energy part of the excitation spectrum. Yes?
So another naive question on the previous slide.
Yes?
So this pattern is like periodic, but then the periodicity is like much larger than you would expect based, like you plotted the Broholm, so based on the crystal structure.
Yes.
So that would imply like there's some periodicity that's much, in real space would be, much tighter, be much smaller lattice than the crystal lattice. So what could that possibly be?
That's a very good point. And what it is that the kagome lattice is not, it's a Bravais lattice with a basis. And so this basis has spacings in it which are significantly smaller than the periodicity of the lattice. And so that's really what we're seeing here. It's really telling us that the excitations have to do with breaking singlets that live within the primitive unit cell of the kagome lattice.
I see. So it would be, somehow from the point of view of the magnetism, it's as if the lattice is made from the little triangles or something.
Yeah, that's right. It's as if I almost don't see the fact that it's linked together to form that periodic structure. And this is an indication that I'm simply breaking singlet bonds between near neighbor pairs. This is the character of the excitations. But this pattern, it's not that if I only had that, then I would expect basically a sharp mode living at the energy that corresponds to that exchange constant. But what I'm seeing instead is actually a continuum of scattering, that extends as far as we could go thus far. So these are very sharp features that just keep going up in energy. So the picture that I should point out this thing here. So this is maybe you could say that's a very dull data set. I just have some sort of constant intensity as a function of energy and as a function of momentum. So it is a little dull, I'll give you that. But it's extremely unusual because what we usually would see is some sort of dispersion relation through this momentum energy space. But I actually have a complete sort of curtain of intensity coming up. And this I don't think we have other examples of that. And it really is what you would expect if I have spin-in type excitations that are moving through a resonating valence bond background. So this is the kind of picture that one would have in mind. This would be the spin half degree of freedom, and it can move through the lattice as it rearranges the singlets. And because motion is requires that rearrangement of singlet bonds, I pick up in the scattering cross section the structure factor of a singlet. So this kind of excitation would have these behaviors. However, there's one thing that's unusual. It was pointed out in this very nice paper by Subir Sachdev and his co-workers that if you simply have this two-particle spin-in process, then at any given momentum transfer, there should be a threshold below which you can't excite any spin-ins, and then above which you can now begin to excite the spin-ins. And this should actually be a pretty sharp edge passing through the system. And this we don't see. We seem to see intensity reaching in some regions of momentum all the way down to zero energy or to very low energy. And what is proposed here is that there is another type of excitation that can exist in the spin liquid on the kagome lattice, which is a Wison excitation. When you create a pair of spin-ins, those can actually interact with the Wison, and you can lose, as a consequence, control even of the center of mass momentum of the pair of spin-ins. And in that way, even though I control the center of mass, I actually can have the threshold energy for creation of spin-ins can drop down because of their interaction with the Wisons. So this is a pretty wild and elegant way of accounting for that. There are features, as Subir tends to point out, in the spectrum that we need to go and look for experimentally, which are the vestiges of these thresholds. And this is perhaps kind of the next challenge we have experimentally, to try to find within the otherwise rather bland pattern of scattering in momentum energy space to actually find these kinds of structures that are predicted. Okay. All right, so any questions thus far on the kagome spin half thing? Yes?
What was this particle you were just talking about?
Wison.
Wison, yeah.
Wison, that's a topological excitation in the Z2 spin liquid, right? Which cannot be created in the scattering process, but which can be part of the underlying quantum state of the system. So